Somewhere on a cold June night in the Andes Mountains, a farmer tilts their head back and studies a small cluster of stars. Not for beauty. Not for ritual alone. For information. Based on how bright those stars look tonight, this farmer is about to decide when to plant an entire season's worth of potatoes, a decision that could mean the difference between a full harvest and a failed one. That sounds like superstition, doesn't it? Stargazing as agricultural planning? Here's the strange part. It isn't superstition at all. It's one of the most quietly accurate weather forecasting systems ever documented, and scientists only figured out why it worked a few hundred years after farmers had already been relying on it. Long before satellites, long before barometers, long before anyone had a word for meteorology, ancient and indigenous cultures around the world were reading the sky, the animals, and the land with a precision that should honestly embarrass you a little, given how much modern technology it eventually took to explain what they'd already figured out. Not through magic. Through generations of obsessively careful observation, refined and tested and passed down until it worked. What makes a forecasting method trustworthy, really? Modern meteorology answers that question with satellites, supercomputers, and decades of grid atmospheric data. But strip all of that away, and the underlying requirement hasn't changed at all. Watch something closely enough, for long enough, and check your predictions against what actually happens. Everything else is just the tooling. The cultures in this video didn't have the tooling. What they had instead was time, attention, and an unwillingness to guess when their food supply was on the line. Start with those Andean stargazers, because their method is the strangest one on this list, and also the best proven. For centuries, farmers across the high plains of Peru and Bolivia have watched the Pleiades, a compact cluster of stars, around the time of the June solstice. If the stars look bright and numerous, farmers expect good rains ahead and plant their potatoes early. If the cluster looks dim or hard to make out, they hold off, bracing for a drier season. Why would starlight have anything to do with rainfall on the ground? In the year 2000, a research team led by anthropologist Benjamin Orlove, working with atmospheric scientists John Chang and Mark Kane, decided to actually test this, using satellite data on cloud cover and atmospheric moisture. Their findings, published in the journal Nature, confirmed something remarkable. In El Niño years, a climate pattern that typically brings drought to this part of South America, the upper atmosphere fills with a thin layer of high-altitude cirrus clouds, so faint you'd never notice them directly. But that faint haze is exactly enough to blur out the fainter stars in the Pleiades cluster. How thin are we talking? Thin enough that you could stand outside on a clear-looking night and never suspect anything was different. These aren't storm clouds. They're wisps, high above normal weather, invisible to the naked eye during the day and only barely perceptible at night, and only if you know exactly where to look and exactly what you're comparing it against. The Andean farmers weren't tracking clouds directly at all. They'd found something even more elegant, a star cluster sensitive enough to register that faint atmospheric change as a simple, binary signal. Bright stars, clear air, good season ahead. Dim stars, hazy air, prepare for less. In other words, the farmers weren't reading omens. They were reading atmospheric moisture, hundreds of years before anyone had a name for El Niño, using the most sensitive instrument available to them, their own eyes, pointed at exactly the right patch of sky, at exactly the right time of year. So picture the actual night. A small group gathers outside as the last light fades, breath visible in the cold mountain air. An elder points upward toward the familiar cluster, counting the stars they can pick out, comparing tonight's cluster against the memory of 100 other June nights. Nobody writes anything down. There's a quiet exchange, maybe a few words of agreement or concern, and then a decision that will shape the next several months: plant early, or wait. Now picture that same ritual repeating, year after year, for generation after generation. A grandmother pointing upward, teaching a child which nights to watch, which stars matter most, how to judge dim from merely different. A bad harvest, remembered and cross-checked months later against what the stars had shown back in June. Slowly, almost invisibly, decades of pattern get refined into something reliable enough to bet an entire growing season on, without a single satellite, without a single degree in atmospheric science, without anyone involved even knowing what a cirrus cloud technically was. Does this kind of forecasting only show up in one place, tied to one unusual coincidence of stars and clouds? Not even close. Similar star-based forecasting shows up independently across Polynesia and Mesoamerica too, different cultures, separated by oceans, arriving at strikingly similar methods simply because the same stars and the same atmospheric physics were available to anyone willing to look up carefully enough. That kind of independent convergence is usually a good sign that something real is being detected, not imagined. In northern Australia, Aboriginal communities developed something entirely different, detailed seasonal calendars built not around a fixed set of months, but around observable shifts in the living world itself. Researchers Suzanne Prober, Michael O'Connor, and Fiona Walsh, documenting this traditional knowledge, describe systems where the flowering of a specific tree, the arrival of a particular bird, or a shift in wind direction each signal the true start of a season, sometimes with more local accuracy than a standardized calendar ever could. Why would that beat a calendar with a fixed date on it? Because a calendar date doesn't know what's actually happening on the ground in any given year. A season that arrives 2 weeks early or 2 weeks late still triggers the exact same date on a printed page, telling you nothing useful. A tree doesn't have that problem. It flowers when conditions are actually right, responding to real accumulated warmth, real rainfall, real soil moisture, not an arbitrary number on a page. Learn to read that tree closely enough, generation after generation, and you've built a forecasting system that recalibrates itself automatically, every single year, without anyone needing to adjust anything. These calendars often stack multiple signals together for confirmation, the way a modern forecaster might cross-reference several data sources before committing to a prediction. The blooming of one plant alongside the appearance of a particular insect, alongside a shift in the behavior of local birds, together forming a pattern far more reliable than any single sign alone. Miss one indicator, and there are still 2 or 3 others quietly confirming or contradicting it. Now travel to the arid mesas of the American Southwest, where the Hopi developed forecasting methods tied just as closely to careful, repeated observation, but built around an entirely different set of signals. Cloud formations gathering over specific mesas were read as signals of incoming rain, their shape, their height, their direction of drift cross-referenced against decades of memory about what similar formations had produced before. Desert animals, particularly snakes and lizards, whose behavior shifts subtly with changes in humidity and barometric pressure, were tracked as living instruments, sensitive to atmospheric changes human skin often can't detect at all. A lizard doesn't know it's forecasting anything. It's simply responding to pressure changes in its environment the way its body has evolved to. But watch enough lizards, over enough seasons, and their unconscious behavior becomes a signal every bit as useful as a modern barometer, translated through observation instead of a mechanical needle. What ties all 3 of these systems together, despite the wildly different continents, climates, and signals involved? None of them relied on a single indicator alone. Andean farmers cross-checked star brightness against memory of past harvests. Aboriginal calendars stacked plant, animal, and wind signals together. Hopi forecasters combined cloud reading with animal behavior, layering evidence the same way a careful modern scientist layers multiple independent data sources before trusting a conclusion. Redundancy, it turns out, isn't a modern invention either. Here's the twist that should genuinely surprise you: none of these systems were guesswork dressed up as wisdom. Every single one of them functions as a real, testable scientific method. Careful, repeated observation. A hypothesis, refined generation after generation. Predictions checked against outcomes, season after season, and adjusted when they failed. That is, in every meaningful sense, the scientific method, practiced continuously for far longer than the phrase scientific method has existed. So why don't these systems get called science? What made these systems different from a modern research paper wasn't the rigor. It was the storage medium. There was no institution keeping written records across centuries. No journal archiving results for future researchers to check against, no peer review, no citation trail leading back through generations of prior work. Instead, the data lived inside people, in songs built specifically to be memorable, in stories structured so each detail stuck, in ceremonies that doubled as scheduled moments to pass exact knowledge to the next generation, at the one time of year it was needed most. Forget it, misremember it, or fail to pass it on accurately, and the system itself would begin to fail within a single generation. That fragility is easy to miss if you only picture the sky, the trees, the animals. The real technology here wasn't the stars or the clouds. It was memory, organized with startling precision, and trusted with something as consequential as an entire community's food supply. A library that could burn down not through fire, but simply through one generation failing to listen closely enough to the one before it. How many of these systems have already been lost that way, quietly, before anyone thought to write them down? Nobody knows the full answer, and that's part of what makes the ones that did survive worth taking seriously. Every system still practiced today is a version that survived hundreds or thousands of years of exactly that risk, tested not once but continuously, by the only judge that ultimately matters, whether the harvest came in or not. So the next time a weather app buzzes on your phone with tomorrow's forecast, consider what that convenience actually replaced. Not primitive guesswork. A living, oral, endlessly rehearsed database, refined over unimaginable spans of time, holding patterns precise enough that a modern climate scientist, decades and continents removed from the people who built it, can run the satellite numbers and confirm, they weren't guessing. They were right, and they've been right for longer than most written languages have existed. Your phone's forecast comes from satellites, supercomputers, and decades of accumulated atmospheric data. Theirs came from something slower and, in its own way, just as demanding, a willingness to keep watching the same patch of sky, the same trees, the same animals, for centuries, and to trust what patiently accumulated observation was trying to tell them. Both approaches, in the end, are answering the exact same question the same way, not by guessing, but by watching closely enough, for long enough, that the pattern eventually reveals itself. Somewhere on a cold June night in the Andes, a farmer is still tilting their head back tonight, checking the same stars their grandmother once pointed to. Not out of nostalgia. Because it still works, and because somewhere underneath your own weather app, in a satellite quietly measuring the exact same cirrus clouds that blur out those stars, the very same physics is still running, whether anyone chooses to look up and notice or not.